Today's problem is allocate minimum pages. Difficulty is medium. I'm surprised the difficulty is not hard, to be honest. I mean, well, the average time's 35 minutes. That's high. And accuracy is 35%, which is low. But I don't know. In principle, it's in principle, it's pretty clear what we want to do. In practice, it's maybe not that hard to figure out how to implement. But given an array of integers where each element represents the number of pages, well, each element array at I is the number of pages in the ith book. So it's really an array of books. An array of the number of pages in books. You also have an integer k representing the number of students. The task is to allocate books to each student such that each student receives at least one book. Each student is assigned a contiguous sequence of books. No book is assigned to more than one student. All right. Objective is to minimize the maximum number of pages assigned to any student. In other words, out of all possible allocations, find the arrangement where the student who receives the most pages still has the smallest possible maximum. Okay? If it's not possible to allocate books to all students, return -1. That's an edge case. They kind of waste one of the examples on showing you what the edge case looks like. So k is 5. Remember, k is the number of students. Now there's only 3 books. If you have 3 books and 5 students, you can't give a book to every student. It's required that each student get at least one book. So in a case like this, -1. And then we'll look at the other example also. Array size is between 1 and 10 to the 6th, 1 million. The number of pages in each book is between 1 and 10 to the 3rd, 1,000. Number of students, which is k, is also between 1 and 1,000. Expected complexity of n times log of the sum of the array. Okay, so that's a tip-off that we want to do a binary search over an answer range. The answer range being the, well, actually we'll talk about what the answer range is. Auxiliary space 1, company tags, quite a lot. Many of which I've heard of, except Code Nation. I'm not sure what that is. Searching, divide and conquer algorithms. Yeah, it's divide and conquer in the sense that it's a binary search, but okay. Yeah, so what do we want to do with this? Well, so first of all, this is kind of like one that we had previously, which was, what is this one doing? This is minimizing the maximum. The other one was maximizing the minimum. So select k elements from an array and maximize the minimum difference between any of the numbers. And the approach was the same, where we define a search space. Search space in that would be the maximum number minus the minimum number. It'd have to be somewhere in that range. And then, we binary search the answer space, and for each possible answer, we're going to need a helper function to tell us whether or not that answer is actually feasible, and then we converge on the correct answer. So, same thing here. Let's see. N is array dot length, the length of the array. If k is greater than n, that's the edge case. More students than books, return -1. Then we have low and high. We need to determine the low and high of the search space. The high is like if every book is assigned to one student, then that would be the sum of every element in the array. So that's what we have here. We're going to go through, we're going to iterate through the array, add the number of pages, and that'll be the high. The sum of every element in the array. A low is the max of any one book, because each student has to get at least one book. So so one student is going to get the book with the most number of pages. So that is the floor on the minimum maximum. So in this case, for example, example 1, the search space would be from 90. It can't get any lower than 90. And it can get as high as, it looks like, if that says 113 plus 90, 203. So somewhere between 90 and 203. Okay? Let's see. Set the answer initially to -1, and then we start the binary search. We find the midpoint, and then we have this helper function. That's really where all the action happens. We get the midpoint of the answer range, midpoint of the search space, and then we check and see, is it possible for this answer to be the correct answer? And if it's well, I mean, there's a couple of possibilities. One is that the answer is too low, in which case it's not possible, and then we would change the low pointer to be mid +1, and we would research the top half of the range. Another possibility is we run it and it says, yeah, it's possible that could work, but you know, there might be a smaller number that would also work. So in that case, we don't stop the search, but we keep track of the best answer that we've seen, which would be the midpoint, and then bring the high pointer down and binary search the lower half to see if we can find a better answer. This really converges too slowly to go through a full walkthrough of the problem, but let me kind of set this up so that we can see everything, and we'll go through a couple of iterations so you can see what's happening. All right, I can't get quite everything that I want here. So this is our binary search loop here, starting on line 19. The important part here is, all right, so there's the mid. Yes, we've got that. We've got almost everything that we want to see here. The only thing that's missing that we can't see, let me get a pen. Is the return here. Can I scroll this? Hang on. I can't. All right, hold on. Put it back like this. Okay, so after the for loop, we return students required less than or equal to K. All right, fine. Students required less than or equal to K. Go back to the pen. And I'm just going to write that here. Now I'm going to write it here. Students required less than or equal to K. All right. So let's see what we can do here. The search space. All right, low. The lowest possible, what is it called? Minimum maximum is the book with the largest number of pages, because every student has to get at least one book. So, and all the books have to be allocated. Somebody is going to have to get this book, in this case, example 1, this 90-page book, and even if that's the only book that they get, it's still 90 pages. So, let's just put the low here and say low is 90. Now, it's possible that K is 1 and all the books get assigned to one student. So the max, the high for the search space would be the sum of all the books, which is, let's see, this is 113. That's 113 plus 90 would be 203. That is our search space, right? So we're in this binary search. We're going to calculate the mid. What is mid? All right, what's high minus low? 203 minus 90 is 113. 113 divided by 2. 112. 56 plus low. 90. So mid is 1, 4, 6. Okay, so we go into is possible. We have the array n, which in this case is 4, number of books, k, which is 2, and mid, which is 146. Let's drop in here, students required, current student page. What we're going to do is we're going to allocate books to a student until the number of pages that we've allocated to that student is going to go over. Wait a minute. You can't even see that. Can I? Okay, hold on. Well, in that case, let me scoot the frame over so you can see it. Max pages. Mid comes in here as max pages. So if we're going to go over the max pages, we stop and we start allocating books to the next student. All right. So students required. Well, we at least one. Current student pages 0. Iterate through the book array. Pages I does if pages I is greater than max pages, that's a failure right off the bat. That's not going to be the case here. If current student pages plus pages I, it's only 12. Is greater than max pages, which it isn't. Otherwise, current student pages, we'll just add the pages. So current student pages, all right, you just got allocated 12 pages. Next book. Are we over the limit yet? No. All right, so you just got allocated another 34 pages. You are now up to 46 pages. Okay, next book. What if we give you another 67 pages? Are you over 146? No. That would actually be 113. Okay, good. Go to the last book. If we give you that book, are you over 146? Yes. All right, you are over the book, so we need another student. All right, now we're on student 2. Student required, increment current student pages. Current student pages, that student would get 90. That student would get 90. All right, 90. And we're done. Okay, So we follow out of this and we return a Boolean, and that Boolean is the number of students required less than or equal to K? We need 2 students. What is K? K is 2. So this returns true. So this is possible. It's possible that 146 would work. So what we do is we save it, 146, but we look for something better. Okay? And what we look for is we're gonna set high to mid minus 1. Mid is currently 146. And so we'll set it to, but why did I did not mean to erase that. I meant to erase this. All right, so this becomes 145. All right, now, so we go through the binary search loop again. We recalculate mid. Mid equals low, which is still 90. Well, let's do high minus low. 145 minus 90 is 55. Divided by 2 is 27 plus 90, right? It's 117. Well, so you can see we're getting closer to the answer that we want, which is 113. And we drop in here again. All right, let me erase some, let me erase some of this. Okay, I'm going to drop in again. Now, students required 1, current student pages, 0, 4, int I. Pages, there are no pages that are greater than max pages, which is 117. Current student pages is, what's going to happen here actually is the same thing. We're going to be able to allocate 3 books to 1 student because those 3 books add up to 113. But we are not going to be able to allocate the last book. So we're going to need another student, and we are going to allocate to that student 90, and that's fine. We'll drop out students required less than or equal to K. Yes. So we have a new possible answer. It's not 146 anymore. It is 117, and then we are going to set high to mid minus 1, which is 116. 116. All right. Let's do, I don't know, maybe let's do one more here, one more loop through it. All right, so go through the loop again. We're going to calculate a new mid. Mid is low, high minus low. 116 minus 90. 26 divided by 2 is 13 plus low is 103. 103. Okay. Let's erase the stuff down here. Wrong one. Erase. All right, let's go through it. 1 plus 0, 0 pages. So the first, so we're going to allocate you, first of all, we're going to allocate you 12 pages. All right. We go to the next book, 34. We're going to allocate you another 34 pages. Are we over our limit yet, which is 103? No, 46. All right, what if we allocate you another 67 pages? Okay, well, you just went over the limit. So now we need another student. Okay, it's 2. current student pages equals pages, which is 67. All right, we go to the next. Now we're going to allocate you another 90. Well, that also sent you over the limit, and so we need another student to whom we can allocate 90 pages. Well, this is too high. So then what happens is we say, all right, well, 103 is too low. So if 103 is too low, then low becomes mid plus 1, which is 104. And we continue in this fashion. I mean, it is going to converge on the answer. So you can see what we're doing here is defining the search space and then binary searching on the search space, picking the middle number and determining if it is possible to allocate the books so that no student receives more than whatever we have calculated as mid pages. We iterate through the books, we assign them to the current student until we exceed mid pages, and then we move to the next student. And if we can assign all the books to K or fewer students, then the helper function returns true. Otherwise, it returns false. If the helper function returns true, it means that mid is a possible maximum. And so we adjust the high pointer down and try to find an even smaller maximum. If is possible is false, it means that mid is too small and we need a larger maximum. So we adjust the low pointer up to mid plus 1. We also handle the edge case of K students being greater than the number of books. All right. All that being said, let's get rid of this and try. Well, let's do a sanity check on it first. That worked. Although you can't see it. All right, and then submit. Okay. All right, please like the video. Subscribe to the channel. It's free. You will get problems of the day in your inbox every weekday. You won't have to go searching around for them. So that's it, and we'll see you next time.